Well, good morning, everybody. Let's get back to our energy picture. So we have a diagram right here of an airplane, the kind of toy airplane that has a wind-up rubber band. You wind that rubber band up as you spin the propeller, and then you let it go. When the propeller is released, the rubber band's going to unwind, the propeller is going to turn really, really fast, and the plane is going to fly. Or at least that's what should happen. I personally tried making a couple of these, and I wasn't too good at it, all right? My planes didn't fly at first, and then I made modifications and it got okay, but I was never the best at it. But the question is, what type of energy results when the rubber band unwinds and the propeller turns, enabling the plane to fly? Well, we've talked about mechanical energy. That's energy that has to do with objects, whether they're moving or they're held in a certain position. And then we've also talked about the types of mechanical energy, which is like potential, which means energy stored there, or kinetic, the energy of motion. Which of those two would be going on with this plane once the propeller starts to spin? If you think it's kinetic energy, you're right. All right, the kinetic energy is going to be, obvious when the propeller spins. The propeller's moving. Energy of motion is kinetic energy. All right, what's one change that could be made that would make the toy airplane fly at a different speed? Think about that. You make something fly, but you want it to fly faster. How would you do it? Would you change something about the shape of your plane? Would you change something about how heavy your plane is? Would you change its power source? Or maybe the way it takes energy from the power source and makes motion? Would you change something about the propeller? Because you could do any one of those things. If you change the propeller, all right, you could make it a larger propeller so it catches more air, maybe gives you more thrust pulling the plane through the air. You could change the shape of the wings and the body to make it more aerodynamic. Because as we've made airplanes throughout the years, we've changed the way the airplanes look. We've made them so they're more aerodynamic, so they can cut through more air, but still get the lift we were talking about in our pressure unit. Or you could change the type of rubber band. Maybe you could make a stronger rubber band, or a weaker rubber band to make it fly slower or faster. All those things, all right? But if you were to store energy inside this plane, inside that rubber band, there is a way you can get it back. And that's what we talked about before. That goes on to something you already have in your notes, the law of conservation of energy. Energy can't be created or destroyed. It just changes form. Okay? So as you store energy in the plane, it really doesn't go anywhere until you let that plane go. You can't destroy the energy. You can't create it. You just take energy from yourself, spin the propeller up, and then the propeller unwinds, pulling it through the air, and it's using up the energy you put inside of it. All right, we even learned how to keep track of energy the conservation of energy last time. We kept track of how energy was stored, how is it being used, and we used what I called a LOL chart. All right, we had that in our notes. I want to take us through another example of an LOL chart, and it's using a slingshot. A slingshot I like even more than that other video I showed you where the guy gets thrown up in the air and he has to pull a parachute. This one, I would totally do. I don't think I've ever met anybody who wouldn't want to do this one. So let's take a look, and then we're going to keep track of where the energy is. Our system is going to be a person in a harness attached to some bungee cords. Let's take a look. By the way, as we go through this, you're going to notice, there's a lot of Mountain Dew in this. Mountain Dew totally sponsored this video, no question. There's our first Mountain Dew. I'm going to just keep track while we're watching. That kid's on a Mountain Dew shirt. That kid's drinking Mountain Dew, so that's 3. She's got a Mountain Dew hat. There's another Mountain Dew. We're up to 5, 6, 7, 8, All right, now remember, we're up to 7 Mountain Dews, but remember the system. Oh, wow, a lot of Mountain Dew hats right there. All right, the system is the bungee cords and, the bungee cords and the person. All right, so when we're talking about the energy there, it's the bungee cords and the people. Oh, and maybe whatever they're carrying with them. So if we hop back, let's take a look at one precise moment where they kind of, there we go. That's not bad. Okay. All right. The person started back here. So we can hop back just a little bit. There we go. Back here attached to the ATV. All right. The bungee cords were very, very stretched. I don't know how hard it is to see on your screen right now. All right. What kind of energy is this at that moment right there where they're pulled back? Let's pretend they were just let go of. So they're not moving very fast. What kind of energy is stored in the person and the bungee cords? Let's hop back here and take a look at our LOL chart. First position, person pulled all the way back. It looks like they're being hung up by my bungee cords, but let's ignore that for right now. Remember, we got to keep track. So our system is a person. Got to get a way to write better. Person. And bungee. So for everything I write from this point on, or every graph I do, it's the person and the bungee cords I'm talking about, right? All the energy's trapped there. So what kind of energy was it? Let me get rid of that writing. Well, if you said it was energy stored in the bungee cords, you'd be right. So on our LOL chart, we wouldn't have much in the way of kinetic because they haven't started to move much yet, but they would have quite a bit of potential energy. All right, their total energy, as a matter of fact, would be potential. These should be about equal. Looks like I made them a little uneven. But when we start off, well, there should be some thermal energy here too. That's why I made them a little uneven. I don't know what happened to my thermal energy. There should be a little bit of energy right here too. Because if you add the thermal energy to that potential, you get the total energy. Why is there thermal? You stretch a rubber band, the rubber band gets hot. The bungee cords are the same thing. You stretch those out, they're starting to get warm. They take some of that energy. All right, our next look, our next shot would be when this person moves forward. Let's try and slow that down. Here they go, flying forward. Ooh, that sounds weird. To right about there. When they're in between these two poles, they are moving quick. All right? They're moving incredibly fast at that point. All right? And because of that, their energy is no longer potential. As they move fast and move forward, in between, they have thermal energy because, we stretch a rubber band, we let the rubber band go. Each time that rubber band moves, it's going to get hotter, so we have more thermal energy. They're still in the air a bit, so there's still a little bit of potential. But most of this potential energy is now kinetic. Energy has transformed. It's gone from one type to another. If we add this plus this plus this, we'd get our total energy, our total mechanical energy. All right, and if we take another look, let's flip forward again. What happens after they go through the middle? Well, obviously, they get stretched out and stopped on the other side. And I turned the music off so we won't have to hear the weird sounds. And notice they stretch out and look, their body's trying to keep going. Why? Because of inertia. Their body's getting carried forward because of Newton's laws. But the bungee cords are applying a force, stopping them, pulling back this way. As the bungee cords stop them, as they do work, they store energy back inside the bungee cords. All right, so when they're on that side, the energy goes back into the bungee cords. All right, they stop moving, so there's no kinetic. The bungee cords are stretched again, so a lot of it becomes thermal energy and a little less potential energy stored on the inside. Once they stop moving, they're going to start moving back towards the middle again, which is what's happening right here. They're flying back, but guess what? They're not flying as fast as they were before. So when they get back to the middle, so there's shoot from here to here. Now they're back to the middle again. What was left of this potential energy? Now some of it gets converted back into kinetic, but less kinetic. Why? Because every time those bungee cords stretch and release, they get hotter. So we're losing kinetic energy, losing potential energy to thermal energy, but the total energy does not change. And for the most part, I mean, that kind of makes sense. After they fly forward again, they're going to fly back to the center and stretch back this way. But they won't go as far as they were the first time. They'll stop moving, and then they'll bounce back again. Every single time they go back and forth, they don't go nearly as far because this thermal piece is building. It's like stealing energy from the kinetic and potential. Which is why the next time they go back to the middle, they're going a lot slower. Thermal increases. They're probably hitting a whole lot of air with their bodies, so they're actually getting a lot of friction. So they're losing energy to the air they're pushing around too. And eventually they stop moving. So that's us keeping track of the energy transformations all the way through this like fun bungee slingshot. And I don't know about you, but I would totally do this one. Now that we've talked a little bit more about how energy will change forms, let's talk about how we measure that energy. Two simple ways we're going to cover them really quick before these notes are over. All right, so you need to write this down. The first way we're going to calculate and get actual numbers for energy is by keeping track of kinetic energy. So I would like you to write down that kinetic energy, the energy of motion for an object, is equal to half that object's mass multiplied by its velocity squared. So when you're talking about the kinetic energy of something, you are talking about a moving object. All the particles put together in that object make up its mass, so we have to have a measurement for its mass. We take half of that, and then we multiply it by the velocity of the object, its speed in a given direction. Remember, you're going to multiply velocity by itself first, then multiply by this piece. So let's take a look at something pretty easy. A cheetah. All right, cheetahs run incredibly fast. So as a cheetah's running, it's got all of its body in motion. All of its, all the muscle tissue, all the teeth, the claws, they're all moving with the body of the cheetah, and the body of the cheetah is going to have a kinetic energy. So if we give it a few numbers, like 40 kilograms for its mass, and its velocity is 30 meters per second, we could figure out the cheetah's kinetic energy. And that's what we're going to do. I'll just freeze that right there. And I'd write out the equation like this. This is what I'm going to ask you to do in your homework. You simply determine the right numbers for the right part of your equation. So kinetic energy is 1/2 the mass of the cheetah. All right, well, what is kinetic energy of a 40 kilogram cheetah? 40 kilograms, there's our mass. A 40 kilogram cheetah is going to be like 110 pounds, in case you're wondering. I just got to write the units down here. If we lose our units, we won't know what we're talking about as far as energy. Okay, or as far as what the number actually means. And then we're going to multiply it by 30 meters per second squared. Per second, and that squared, that's not part of the units. It's not like acceleration. It's actually something we're going to have to do to the number. Okay, so order of operations, always square first. 30 squared, 900. Okay, so I'm going to have 900 meters squared per second squared. Then we take the 1/2 times 40, that's 20, so 20 kilograms times 900 meters squared per second squared. We're going to get 18,000. Let's see here. 18,000 is going to be kinetic energy of the cheetah. And if I haven't said it before, when we're measuring energy, we have a unit for energy. It tells us exactly how much work can be done. And the unit is joules. Capital J O U L-E-S. That's the unit for energy. We'll just usually use capital J. It makes things a lot easier. So what does that mean? Well, that means if this is your pet cheetah and you have your pet cheetah running across the desert plains towards you and it's speeding and jumps up and you're going to give it a big bear hug, that's a big mistake. All right? As that thing jumps into your arms, it's going to deliver 18,000 joules of energy to you, which is going to break your bones. All right? When cheetahs hunt, yeah, they have teeth, yeah, they have claws, but really, they tackle things. They tackle things and deliver all this energy to them, making it hard for them to run for a second, and that's when they sink their claws in. So, a lot of energy. Watch out, okay? That's kinetic energy. Kinetic energy is equal to 1/2 the mass of the object times its velocity squared. The next thing we'll learn how to measure, beyond the cheetahs, is going to be potential energy. So we have a situation right here where we got a bridge. Maybe somebody's on top of that bridge going to go bungee jumping. Now maybe you don't know what bungee jumping is, so I'll show you real quick, but you have a person in a very high position. They're attached to a very stretchy cord. That's our bungee cord we've been talking about. And they simply are going to jump off that high place, let gravity pull them down, and then this cord is going to stretch out, stop their motion, and then pull them back up. And then they're going to get up high again, not as high as they originally were. Then they're going to fall back down. The cord stretches out, stops them, and it kind of goes back and forth until they stop moving. And it looks, well, it looks a little crazy. Take a look at this guy. He's jumping off of a dam. All right, he's actually going to throw a tennis ball and try and catch the tennis ball. But he's doing it by bungee jumping. At this point, he's really high above the air, but he's not moving. So all of his energy is going to be stored energy. Again, potential energy. His energy has to do with his mass, just like the cheetah, its energy as it was running had to do with its mass. But now it's like where the mass is. In this case, his mass is really high above the ground and has the potential to fall. Now let's take a look. He throws a tennis ball, jumps, and he tries to catch it. But he freaks out a little bit, loses track of the fact he's going after a tennis ball, and just focuses on not passing out from the excitement. The tennis ball's right there. He kind of missed it. He stops moving, and then he's going to get pulled back up. So he missed it, but that happens. All right, now how do we take care of this and calculate his energy? All right, so energy, in this case, potential energy, has to do with mass, gravity, and height. So how do we find this, this jumper's potential energy? We have to know the sum total of all the particles in their body, their mass. We multiply it by how gravity accelerates things on Earth. And if you remember, it was 9.8 meters per second squared. And then we just have to know how high in the air is this person. So for this fictional jump, we have a bungee jumper who's 500 meters above the ground. That is really far, 1/2 kilometer. That's a huge jump. Maybe the dam wasn't that big, but let's pretend. All right, then we have to know something about the jumper, their mass. So 60 kilograms, maybe about 180, 190 pounds. All right, and then how does gravity pull on them? 9.8 meters per second squared. And we write out our equation. So we're just substituting in to find the energy of the bungee jumper in joules. So potential energy is equal to mass, 60 kilograms, multiplied by gravity, that's 9.8 meters per second squared, again, in this case, the squared part is actually, you are not actually squaring the number, that's just part of the units. And then we have the height in the air. In this case, that height was 500 meters. All right, so to find the energy of the bungee jumper, to find how much work they could do on something if maybe their bungee cord did not stretch properly or snapped, and they had to fall and hit something down there, how much work could they do on that thing? It's going to be 60 kilograms times 9.8 meters per second squared times 500 meters, and it's all going to be measured in joules in the end. Multiplying out, the potential energy of this bungee jumper is going to be a really, really big number. It's going to be 294,000 joules. Way more than that cheetah. Yes, the cheetah was running fast, but that person is falling even faster. And that's even more mass than the cheetah had. Alright, so your bungee jumper is going to have more energy than your sprinting cheetah. You don't want to be hit by either one, trust me. That's how we measure and calculate energy, at least those two forms. And those are the two forms I'm going to keep you using, kinetic and potential energy. So please take notes on this. Make sure you've taken some notes on this, and they will help with your assignment. Have a good day.